This presentation is on the hourly electricity demand and price forecasting that was done for the New South Wales, a province in Australia. The goal is to provide reliable short-term forecast to support trading, desk decisions and generation scheduling, and then to increase operational efficiency. So our data overview, the source of our data was the Australian Energy Market Operator website. The granularity, there were 5-minute dispatch data, which were aggregated to hourly observations for computational efficiency sake. And then the study window covered 4 months, November 2024 to February 28, 2025. So the first 2 months, November and December, were used as the training set. Then January, February were used as a validation set, and then the two were recombined as a test set. Now the variables included total demand, the original reference price, date and time, and there were 2,880 rows altogether. The exploratory analysis that were done include outlier detection, ridgeline plots, and STL decomposition. So for outlier detection, we use the IQR model as our fences. So you can see that for hourly demand, there are outliers that are extreme values, which are outside the upper limit of the fence, and then also the lower limit of the fence. And then for the hourly price, we have outliers that are outside the upper limit of the fence. Then ridgeline plots. So we use a ridgeline plot instead of the traditional time series plots because of our data points. We had a lot of data points, thousands of them, and using the time series plots made them cluttered. So the ridgeline plot helped to compress thousands of hourly traces into 24 intuitive density snapshots, letting us spot peak hour volatility and then midday negative price events. So that's what we did. So if you look at the hour of day demand and price from 0 to 6 hours, that's the deep blue over here, and we have the narrow low mean curves, so which means that it's quite overnight load, and then when the price also is about $60 to $120 per megawatt hour. So if you look at that, also you see the morning ramp. Yeah, it widens over here, so it means more people, the demand is high, more people are using, and then it goes on that way. For the STL decomposition demand, STL separates each series into trend, daily, seasonality, and remainder, so that we know what each model component must tackle. So for the daily parting, it dominates both price and demand. So that validates our use of hour of day predictors, as you can see the hourly distribution, etc. that were done. And then you can also see that the trend is smooth. So a simple spline, this is the trend, a simple spline or first difference is enough, so there is no need for high ordered polynomials. Then the price remainders are volatile, which justify the rensorization, that is the capping of the outliers, and then wide prediction bands. So for this, you can see the weekday pink in the middle, the weekends at the ends, and you can see that the weekday has more demand than the weekend, with Sunday having the least demand. Then with the price also, the weekday is blue in the middle, and then weekends orange at the end, with again the weekends having less the least prices in comparison to the weekdays. Now, in conclusion, we can see that from our EDA, there are pronounced daily and weekly seasonality, and Sunday evenings have the least demand. Then we can see clear price spikes which coincide with peak demand like normal economics, and then no strong multi-collinearity between engineered calendar features, as you see later. So for our modeling workflow, we started with a naive as our baseline, And then we also used the multiple linear regression. Then we did also an ARIMA. So with the both with all the three, that's naive, linear regression, and then the ARIMA, what we did was to create a model based on the raw data sets after aggregation, which is a form of transformation. And then after doing that, we realized that the best performing one was the ARIMA with 1.37, followed by the linear regression with 1.38. Then we went ahead to Winsorize. So Winsorize is capping your outliers. And so we capped our outliers, and after capping it, we realized that the multiple linear regression did better for 1.36, whilst the ARIMA did not change. So we went ahead with the linear regression. There's some extra transformation, like we build some interaction terms, that's hour of day and then the day of the week, so hour of day, whether it's a weekday or it's a weekend. And then we also looked at some holidays, and then we also um, looked at some box cost transformation for the price. So those are some of the things we did. And then at the end, it did well, but not too significant. So to tune the model, we decided to introduce Ridge and Lasso to regularize. And so with the Ridge and Lasso, what we did was to first scale all the predictors so that we will be able to withstand the penalties for the Ridge and Lasso. And then afterwards, we evaluated using the maze. So the maze was done on the validation set for all of them. And then we also looked at the model performance for the recombined set. So after all the transformations, etc., we went through again. So this was repetitive. So you do one stage and then go back to redo for whatever you do, so that you put all on the same scale and apply every model to ensure that you are doing whatever is fair to get the best model. So after doing that, we realized that the maze for the naive came to 1. The linear regression was 0.84 before mensurization and 0.79. The ARIMA maze went to 0.76, but then the Lasso did better at 0.685 for demand and a 0.60 for price. So in order to also prevent overfitting, what we did was, as you can see, there was partitioning of the data. So we split the data sequentially. We did a 2 months for training, 2 months for validation, and then we put them together. We also looked at we also looked at winsorizing the extreme prices. So we cut the prices, and then we also did the benchmark comparison to the naive to also ensure that we mitigate overfitting. Then we also looked at predictor contribution analysis to be able to tell what predictor did what. So in the first column, it shows the individual power of the predictor when added to the model. And then this one is also the marginal importance of that predictor once every other predictor is in place. So the first column, if it has a lower maze, then it means that it did good. And then the change in maze here after it was added to the final model, if it has a greater change in maze, then it means it did better. So you realize that the change was just marginal. It was just marginal, nothing extraordinary about these predictors that were used. And then the diagnostics we looked at was the actual versus fitted values, residual plot, and then the ACF of the residuals. So with the actual versus fitted values, the Lasso model tracked observed demand and price values closely over time. The series visual. So if you look at the demand, the blue fitted line almost sits on top of the gray actual for most of November to February. So the model tracks day-to-day swings and the evening peaks very closely. So it peaks above 120 gigawatts and troughs near 60 gigawatts. But then the tallest spikes are clipped. So you can also see that largest weather-driven surges will still create approximately about 6% under prediction, which is acceptable for electricity operations. And then if you look at the price, the overall shape of the price, you can see that it is high in November to December and lower in January to February. Now, if you look at the residual plots, you can see that the residuals hover around zero the whole period, which shows that it's unbiased. And there is no obvious pattern, so there's no trend or seasonality left here in the errors. So the model, we can say that the model captured the systematic structure. We do have some variance though, but then we can say that it's acceptable because it's about uh, plus or minus 5%, so 0.05, and which is typical and tolerable. So we also have some event spikes, which we can coincide with extraordinary like events, great events, which we can also say reminds us that no deterministic model can predict every shock accurately. Then looking at the ACF plots, we can see some residual autocorrelation was observed at certain lags. So then this suggests that although the model is strong, some patterns still remain unmodeled. So there's room for further improvements, which we can look at incorporating for especially when it comes to the volatility specific things that we have like electricity, like the grid issues, weather issues, etc., temperature. So our final forecast and interpretation was that we adopted the lasso, which regularized the regression for operational deployments, and then we looked at our hourly MAA at 160 megawatts, and then the price is 9 megawatts hour. So from there, we can see that the forecast error was largest during unplanned outages and then price cap events. So our recommendations and our next steps is to automate daily ingestion and retraining pipeline to integrate temperature forecast and demand response signals and to publish interactive dashboard for stakeholders. Thank you.